looking at Qz15, common ion effect. Okay. And complex. And now, the salt in the presence of a common ion will have a higher solubility, a lower solubility, or solubility will be unaffected. Lower solubility. Right. So, common ion basic function is to reduce extent of reaction, and in the case of salts, that would be the solubility. And if you had a common ion with an weak acid or a weak base, what would that do? If I had a weak acid or a weak base, how would that affect the pH? If I had a weak acid, the normal pH would be lower or higher? Yeah, so normal pH would be lower because you get more ionization out of it, okay? So if you put a common ion, you'd get less ionization, and that would push the pH up, okay? So here, I said the normal pH, is it higher or lower? Yeah. Okay, so a weak acid, common ion, function to increase pH toward base range, basic direction. And same way with a base, it would inhibit the amount of hydroxides delivered into the solution, and so it wouldn't be so basic. In other words, it wouldn't be so high, so it would lower the pH. So common ion lowers pH toward the acid range. And yeah. Say you're given a 0.10 molar acetic acid, and its Ka is, I make it easy, 1 times 10 to the minus 5 right now. And you mix with a 0.01 molar, say, HCl. And so you're providing 0.01 molar in extra hydrogens for the for the weak acid HOAC. So HOAC would be inhibited in its ionization by, initially, we're starting with a 0.10, but we already have a 0.01 and in the solution. So everybody understand the problem? You see the idea? And then the change, and see at equilibrium, this would go down by x, up by x, up by x, and 0.10 minus x, 0.01 plus x, and then x. And in systems which actually are lower than, say, 10 to the minus 4, that's a borderline, 10 to the minus 4, you can drop the x here, so this would be 0.10 molar at equilibrium, 0.01 molar at equilibrium, and so X would tell you the extent of ionization in there. Actually, I should have gotten a sodium acetate in this thing instead of an acid. Why don't we do that? Let me try that in a different context, because I was talking about pH. Sodium OAC. Just changing the. Now we got it. Molar in the HOAC. Now, pH of the HOAC without the, let me grab here, would be simply hydronium ion square root of Ka, which is 10 to the minus 5, and concentration is 10 to the minus 1, and so 6 square root of 10 to the minus 6 is 10 to the minus 3, and so that would give you a pH of 3. Okay, minus log of 10 to the minus 3 is 3. Okay, so let's calculate the X value, find out what the hydrogen is, and so that would be Ka equals hydronium ion, OAC ion over HOAC. Okay, and so we're looking for the hydrogen ion, and so that'd be Ka times HOAC, that look like an H in there, divided by the OAC concentration. So that's 10 to the minus 5, 0.1, yeah. 10 to the minus 1 divided by 10 to the minus 2, and so 6, add back to 10 to the minus 4, so this pH would be 4. So it's increasing the pH because it's not delivering as much hydrogen into the solution. So this would be a good one for you to check into as it affects the ionization from normal to common ion effect. Okay, and this one, you're given the formation of a complex ion and its formation constant. What is the dissociation constant? How do you calculate that? Anybody? So the Kd is equal to 1 over K formation, which is 1 over 1.7 times 10 to the 7th, and I got 5.9 times 10 to the minus 8 in terms of dissociation constant. Now, there will be occasions on the test where you'll have an equation, and to make it work according to the problem, you'll have to turn it around. And then you calculate the K value that is associated with the reverse reaction. So remember, just simply take the reciprocal of the given forward reaction, and you get the reverse reaction. And that's C choice. Any questions? Okay. Which of the following has the greater solubility? Well, all of them were 1-to-1. Therefore, can use Ka value. Okay. If they're not all the same ratio, just for note, you have to use the ionization or solubility formulas. And for a 1-to-1, X is the square root of KSP. For a 1-to-2 or 2-to-1, X is the cube root of KSP over 4. For a 3-to-1 or 1-to-3 ionization, X is the fourth root of KSP over 27, and for, say, a 3-2-2-3, which is the extent of what we have in our textbook, X is equal to the fifth root of KSP over 108. And so it's to your advantage to learn these in that context. You will have problems which will not be 1-to-1 all the way down. I do 1-to-1 here for time's sake, and hopefully you remembered that. And then you just get the larger value. 10 to the minus 3 was obviously the larger one. That's silver acetate was the This KSP was equal to 2 times 10 to the minus 3, and was the larger of the collection in your answer choices. So everybody okay with that? It's very straightforward, but you got to certainly know if you have mixed ionizations, you got to use the formulas. Okay. Okay. Iron hydroxide ionizes in water to deliver iron 2 and 2 OHs. So any compound which will increase or deliver extra irons, or any compound that will deliver any extra hydroxides before you put in your primary salt is a common ion. So we gave you FeNO3, and it will ionize to Fe plus 2 NO3s, and yes, that's a common ion. And sodium hydroxide, we know, is sodium plus the hydroxide, and yes, that's a common ion also. And ammonium hydroxide will do the same. Now this was a weak base, so, but it still delivers some of the OH, not as much as the sodium hydroxide at equivalent concentrations with compound. But anyway, so this D choice, or all of those, will provide a common ion in that iron hydroxide mark. And finally, number 5. You're given silver chloride and KSP value. What's the salt solubility in the presence of 0.1 molar HAl? So we write the equation. Silver ionizes and chloride right there initially. See, I gave him HCl, so it'd be here, so we're going to have a 0.01 molar chloride before we put anything in. And so change in concentration equilibrium now would be plus X, and 0.01 plus X, which is 0.1 molar, as shown here. Okay, let me pick this up a little bit. Still got it on. Okay, so the KSP expression is silver times the chlorine, like that, and we substitute in the KSP is 1 times 10 to the minus 10, and make them easy, make calculation a little easier. Silver X would be the solubility, and chloride is 10 to the minus 2, and make it easy, molar. And so this would give us X to be 10 to the minus 10 over 10 to the minus 2, or 10 to the minus 8 mole per liter in silver ionization, and that is D choice in that case. All right, stop this one.